Okay, this is section 10.4, and we're going to talk about area here. So it says that if f is continuous and non-negative on the interval alpha to beta, then the area of the region bounded by r, which is a polar equation, and between the radial lines theta equals alpha and theta equals beta, is this integral. Okay, so you got half the integral going from alpha to beta of r squared d theta. So let's take a look at problem 3 here, where it says to find the area of the region inside the lemmason, r equals 2 plus cosine theta. Okay, now as a note, you can draw this entire curve on the interval 0 to 2 pi. Okay, I'm going to use some symmetry here. So by symmetry, we can double the integral if we go from 0 to pi, okay? If I go from 0 to pi, I'm finding this upper half, and then if I double it, I'll find the area of the whole thing that's shown there, okay? So there's a half in front of this integral. I'm going to double that, so that's gone. And we're integrating from 0 to pi. R is 2 plus cosine theta. I'm squaring r, and then stick a d theta at the end. Okay? When I square 2 plus cosine theta, that's 4 plus 4 cosine theta plus cosine squared theta. Okay, I can get the first two antiderivatives here right off the bat. For cosine squared theta, I'm going to want to use a power reducing formula. Cosine squared theta is 1/2 plus 1/2 cosine 2 theta. Okay, and so that's what I got right there. I'm factoring out 1/2. And then I can get the integral. Okay, so the antiderivative of 4 is 4 theta, then plus 4 sine theta plus 1/2 theta plus 1/2 cosine plus 1/2 sine 2 theta, times 1/2, that's 1/4 sine 2 theta, and you're going from 0 to pi. Okay, plug in the bounds then. You got 4 pi plus sine pi is 0, sine 2 pi is 0, and then 4 pi plus pi over 2. And then when I plug in 0, all these 4 terms here are going to be 0. So I got 4 pi plus pi over 2, that's going to be 9 pi over 2. Okay, that'd be the area of this shaded region here in the picture. Okay. Now, as a note, most of the time, the radial lines needed for integration that are not the major axes are going to be nice trigonometric angles. So there's like pi over 6, pi over 4, pi over 3. Consider that, when you're trying to figure out the radial lines here. Now, in this problem, I want to find the area enclosed by one loop of the rose curve given by r equals 3 times cosine 3 theta. Okay, so I need to find these radial lines here, or the beginning and end of where I'd shade in this one loop. Now, it looks like if I were to draw radial lines, or tangent lines here, it looks like it'd be pi over 6 and negative pi over 6. Now, I'm just guessing. Okay, I want to know for sure. So if I plug in pi over 6, cosine of 3 times pi over 6, that'd be cosine pi over 2, that's 0. And then if I plug in negative pi over 6, I also get 0. Okay, 0 is in between negative pi over 6 and pi over 6. So if theta is 0, cosine of 0 is 1, right? So r would be 3. Okay, and that put me right there at that point. So I'm going to completely trace out this loop here on the interval negative pi over 6 to pi over 6. Okay, and I want to find the area of that shaded region. Well, it's going to be half the integral going from negative pi over 6 to pi over 6 of r squared, there's r, d theta. Okay, so 3 squares is 9, I can factor out a 9. And I got cosine squared 3 theta inside the integral. Let's see, I'm going to use the power reducing formula for cosine squared 3 theta. That'd be the same as 1/2 plus 1/2 cosine 2 times 3 theta would be cosine 6 theta, right? I got a 1/2 coming out at the integral, so that'd be a 9/4 there. And using that that power reducing formula, I can now get the antiderivative. So the antiderivative of 1 is theta, plus the antiderivative of cosine 6 theta, that'd be sine of 6 theta divided by 6. Okay, you plug in the bounds next. So when I plug in pi over 6, sine of 6 times pi over 6, that'd be sine pi, that's 0. And then when I plug in, when I'm subtracting a negative, pi over 6, so that'd be plus pi over 6, plus 1/6 times sine of 6 times negative pi over 6, that'd be sine of negative pi, that's 0 also. Okay, so I got 9/4 times pi over 6 plus pi over 6, that gives me 3 pi divided by 4, which would be the answer to the shaded region there. Okay, now there's a note which is very important here. It says to find the area of the region lying inside all 3 petals of the rose curve, you would not just simply integrate from 0 to 2 pi. In doing this, you would obtain 9 pi over 2, which is twice the area of all 3 petals. The duplication occurs because this entire curve is traced twice on the interval 0 to 2 pi. So, you know, I mentioned that a lot of the polar graphs can be traced out one time on the interval 0 to 2 pi, but not all of them, like circles, for example. I can draw a circle on the interval 0 to pi. Okay, so consider that. Like, so the point of me saying that is because you want to check the values of theta. Okay, your start and end points on the integral. They're don't assume anything. Okay. Problem 5 is where we want to find the area of the region lying between the inner and outer loops of the lemmason 1 minus 2 sine theta. Okay, I'm going to let A sub 1 be the region lying inside the inner loop, this guy here, this little region there, and A sub 2 would be the region lying inside the outer loop, so this guy here. Okay, now I need to find their radial lines here, the start and end points. Now it looks like if I draw a radial line or a tangent line here, it looks like it'd be pi over 6 or maybe pi over 4. Okay, so let's try pi over 6. If theta is pi over 6, sine of pi over 6 is 1/2, times 2 is 1, and 1 minus 1 is 0. Okay, so I'm going to be starting here at pi over 6, and by symmetry, this other radial line would be 5 pi over 6. So the inner loop, this little guy here, is traced from pi over 6 to 5 pi over 6. Okay, now I'm going to find A sub 1 and A sub 2, and then we'll subtract those two numbers there once we have them to get the answer. Okay, A sub 1, okay, so I'm going from pi over 6 to 5 pi over 6. I need half the integral of r squared. R is 1 minus 2 sine theta squared d theta. Okay, and when I square that out, I get 1 minus 4 sine theta plus 4 sine squared theta. Okay, the first two expressions I can get the antiderivative right away. It's just that 4 sine squared theta. I'm use the power formula for sine squared theta. That's 1/2 minus 1/2 cosine 2 theta. And let's see, 4 times 1/2, that's 2, right? And so I got 2 times 1 minus cosine 2 theta from that part there. Okay, and then I'm going to get the antiderivative next. So I got 1/2 times the antiderivative of 1 is theta. And then the antiderivative of sine theta is negative cosine theta. I'm subtracting a negative, it means I'm adding. 4 cosine theta, okay, and then plus 2 theta minus sine of 2 theta. The derivative of sine of 2 theta is 2 cosine 2 theta, right? So let's see, theta and 2 theta, that's 3 theta, right? So that brings me to this line here. And now I'll plug in the bounds. When I plug in 5 pi over 6, let's see, I got 1/2 times 3 times 5 pi over 6, that's 5 pi over 2, plus 4 times cosine of 5 pi over 6, that would be negative root 3 over 2. 4 over 2 is 2, right? So minus 2 root 3 minus sine of 2 times 5 pi over 6, that'd be sine of 5 pi over 3. Sine of 5 pi over 3 is minus root 3 over 2. And I'm subtracting a negative, so that means I'm adding root 3 over 2. Okay? And then minus, when I plug in pi over 6, let's see, 3 times pi over 6, that's pi over 2. Plus 4 times cosine pi over 6, that's root 3 divided by 2. Times 4 is 2 root 3. Minus sine of 2 times pi over 6, that'd be sine pi over 3. That's root 3 over 2. I'm subtracting a root 3 over 2. Okay, so then the next thing is that when I simplify this guy here, I'm going to get 1/2 times 2 pi minus 3 root 3. Okay? So then the next thing that I'm going to do, and that's the area of this white region, this that's inside the inner loop here. So then the next thing I'm going to do is I'm going to find the area of the region inside the outer loop. Okay? So now I need to start with 5 pi over 6, and I need to trace this around. Now I don't want to end up 2 pi, right? Because if I end up 2 pi, I'll be stopping right there, right? Now I wouldn't get the entire area. So 2 pi plus pi over 6, that'd be 13 pi over 6. Okay? So I'm going to go from 5 pi over 6 to 13 pi over 6, integrating this function here. And so I'll get the same antiderivative as before, right? This guy here is what I got there. And I'm going from 5 pi over 6 to 13 pi over 6. So then when I plug in the bounds, 3 times 13 pi over 6, that's 13 pi over 2. Plus 4 times cosine 13 pi over 6, that'd give me the same answer as cosine pi over 6, which is root 3 over 2, times 4 is 2 root 3. Okay, and then minus sine of 2 times 13 pi over 6, that'd be 13 pi over 3, which is the same thing as sine pi over 3. Sine pi over 3 is root 3 over 2. I'm subtracting a root 3 over 2. Okay, and then minus when I plug in 5 pi over 6. Let's see, I got this guy here. I've already found that. So 3 times 5 pi over 6, that's 5 pi over 2. Plus 4 times cosine 5 pi over 6, that's minus 2 root 3. And then minus sine of 5 pi over 3, that's root 3 divided by 2. Okay, again, just using what I got up here, I'm just copying and pasting right there. So then I get 1/2 times, let's see, it's going to be 13 pi over 2 minus 5 pi over 2. That's 8 pi over 2. That'd be 4 pi, right? And then 2 root 3 plus 2 root 3, that's 4 root 3. Minus root 3 divided by 2 minus another root 3 divided by 2 is 3 root 3. Okay? So then to get the total area of the shaded region here, I need to take a sub 2 and then subtract a sub 1, right? And by removing that unwanted space there, I'll have what's left over, which is what you see shaded in this picture. So a sub 2 is 1/2 times 4 pi plus 3 root 3. And then I'm subtracting 1/2 times 2 pi minus 3 root 3. Okay? So I get 2 pi minus pi, that's pi. And then 3 root 3 divided by 2 minus a negative 3 root 3 divided by 2. That'd be 3 times root 3. Okay, so the answer here, the complete area here, it'd be pi plus 3 root 3 is the answer. And again, you know, just like all these other problems, give the exact value for everything. That's how the answers are going to be in the back of the book. And, you know, that's all I wanted also. Okay. All right, we'll go ahead and stop the video right here. And I'll pick up with the problem 6 in the next video here.